Good morning, everyone, from the PTV headquarters in Karlsruhe. I'm Peter Sukennik, PTV Vissim product manager, and today I want to talk about the CoEXist project. The project itself is funded by European Union, includes 15 partners from 7 countries, and will end this year. The future is automated, but it will not happen overnight. We will have a quite long transition phase where conventional and automated vehicles will coexist, and not just one type of automated vehicles, but probably many of them. And that's why CoEXist exists. The aim of the project is to prepare cities for the transition phase. It is all about AV readiness, AV ready authorities, infrastructure, and AV ready modeling tools. Our role in the project is to enhance, to improve modeling tools, both of them, microscopic and macroscopic. In the project, we rely on 3 different information sources. First one, data collection on the test track in Helmond, Netherlands, with automated vehicles performed by TES International. Second one, we received information from our project partners about expected driving behavior of automated vehicles. And the third one, we performed co-simulations together with the French research institute Vedecom, where an ego vehicle controlled by Vedecom's driving logic interacted with conventional vehicles provided by Vissim. All this knowledge was used to implement new features and propose parameter values for the simulation of automated vehicles. With Vissim, we performed simulations for basic networks like simple link, on-ramp, off-ramp, lane drop, etc., and provided results for the University of Stuttgart for appropriate settings in Vissim, mainly volume delay functions. After that, for project cities, use our software for 8 local use cases with automated vehicles. The first important question for us in the project was, are there differences between conventional and automated vehicles in driving behavior? To find out, we needed data. And that's why we collected empirical data on the test track between Helmond and Eindhoven. We had 3 vehicles in the test. First one controlled by a human, second and third one automated with communication possibilities. We had many test scenarios with different following: gap time, speeds, communication on or off, switching on and off while driving, and so on. And the results show us that there is linear deterministic relationships, headway speed with car-to-car communication, that there is almost linear relationship headway speed when following manually driven car on a or AV without car-to-car communication, that there are oscillations during the following process which are small and without much variance. And with car-to-car communication, the test vehicles were able to drive safely with 0.6 or 0.3 second headway. And large safety distance in dry-away behavior when there is no communication, and no stochastic variation in dry-away behavior. Let me explain some new features implemented in PTV Vissim software for automated vehicles. The pictures on the right show the relationship between vehicle speed and distance to the vehicle in front while following. It is not so difficult to guess which one represents conventional vehicles and which one the automated. There's a lot of stochastics with the human driver and much more deterministic relationships with automated vehicles. And that's why Vissim allows you now to switch off the internal stochastic. Internal behavior model integrates several stochastic values indicating the spread of human behavior, which means the risks risk acceptance, the ability to estimate distance and speed differences, the precision when operating the throttle and braking pedals. And for AVs, deterministic values for these parameters can be assumed. Next feature I want to talk about, it's about sensors and equipment limitations. The idea behind it is that an automated vehicle can see the signals ahead, but only one or two vehicles in front of itself because the sensors cannot see through the leading vehicle. And in Vissim, you can specify the number of interaction vehicles and the number of interaction objects. And the number of interaction vehicles is a subclass of objects. And you can have situations that because of the equipment of the automated vehicle, only the first vehicle in front of the automated vehicle can be seen, but not the second one. And let me demonstrate this in a very simple example. You have a situation with one standing vehicle and two vehicles will approach. One will turn to the right and the second one will continue straight. If the white vehicle can see the green one at the right time, can decelerate on time, and there is no safety problem. But if the green vehicle can see the black vehicle here too late because of the limitation of the sensors, it cannot decelerate on time, it cannot stop at the right position, and it can lead to an accident. So this is how you can deal with the sensor or equipment limitations in your model. We have also headway based on class of leading vehicle, which means that for each combination of two different vehicle classes, you can set few driving behavior parameters. So you can have a smaller gap time for automated vehicle, which is able to communicate with the other automated vehicle. You can have a higher gap time if automated vehicle is following another automated vehicle but without the communication, and another most likely higher time gap or following distance when the vehicle follows a human-driven vehicle. Next feature, a big one, is platooning built-in feature. So you don't need scripts to have platoons inside your models. Under Platoon, we understand here connected vehicles traveling very closely and safely together, possibly at high speeds. The use case is to simulate effects on general traffic, not the dynamics, vehicle dynamics inside the platoon. And we assume stable driving. We implemented also a few new behavior attributes for platooning, and you have the possibility to define platooning vehicle class specific. So you can decide if the cars will build a platoon only with cars and AGVs with AGVs only, or if you would like to have mixed platoons. Both is possible, it's up to you. It's line specific because we implemented a new feature which allows you to define a specific driving behavior not only for each link in your model, in your network, but also for every lane on your link. So you can allow platooning only in one link or two links or in all links or lanes in your link. Some more details about platoons. joining, only vehicles with the same driving behavior can form a platoon, and it's not possible for vehicles which are on public transportation or on a parking routes. We implemented 5 new platooning parameters. First one is the maximum number of vehicles in a platoon you can set. Then you can set the maximum desired speed of the platoon. You can set the maximum distance for catching up to a platoon. You can set the gap time within a platoon and the minimum clearance within the platoon. The platoon will drive with the maximum speed you specify for the platooning or with the desired speed of the platoon leader, always with a lower from these two values. Then driving, platoons do not any lane changes. If a vehicle needs to change the lane, it needs to the platoon needs to be dissolved, needs to split. The vehicles keep the same distance, and there is a limited acceleration change for the platoon members. The parameters for platoonings can change during driving. When a platoon drives from one link to another link, on that second link you can have different driving behavior with different driving behavior values, so you can change the parameters also or set different driving parameters for different parts in your model. The platoon can split at direct signals if needed. If not, all vehicles can make it on a green signal. If a vehicle needs to leave the platoon, the distance to the vehicle in the front and behind will increase and the platoon will split. How it works with the platoon stability. Each platoon has a platoon leader and the last vehicle in the platoon. And this last vehicle in the platoon proceeds to keep defined gap time and clearance to preceding vehicle, while the acceleration for this vehicle is limited to the acceleration of the leader plus minus 2 meters per square second. And for the platoon members, these are distributed equally between the first vehicle and the last vehicle. And there is no explicit simulation of the communication process itself, so no packet sending or dealing with the latency like you have in a real world. We assume stable driving. This is a short demonstration how the platoon works. So you can see that the vehicles adapt the distances based on the speed. When a vehicle needs to change the lane, the platoon splits. Then later, the second platoon can rejoin the first one. So not only vehicle can join a platoon, but also another platoon can join a platoon. Then if not all vehicles can make it through the intersection on the green signal, the platoon will split. Analogically, if they cannot pass through unsignalized intersection where you use the priority rules, the platoon will split, and the same when the vehicles need to change the lane. And after that, when the vehicles are in the same lane again, they can form a platoon again. Platoon attributes which are available. The first one, index and platoon, you might know already, which indicates the position within the platoon. And in the last weeks, we implemented two new attributes. The first one is platoon leader number. If a vehicle is a member of a platoon, this attribute is set to vehicle number of the platoon leader, otherwise it's empty. And the second one is platoon size. If a vehicle is a member of a platoon, this attribute contains the total number of vehicles in a platoon, otherwise it's empty. So if you want to do some traffic management, or you are using scripts for some more complex modeling, and you need more information from each vehicle, you can use these attributes. A few words about the modeling framework. The goal of the traffic modeling in the CoEXist project is to assess how the impact of automated vehicles evolves during the whole period of coexistence of conventional vehicles and CAVs, from the first introduction of small number of automated vehicles until when only a few conventional vehicles remain. And to enable such assessment to a transition period, the transition period is discretized into 3 stages here: introductory, established, and prevalent. And these stages are characterized by AV market shares, which means how common are they, AV capabilities, where can they drive, and AV driving behavior, how do they drive. And the behaviors of the automated vehicles are specified by driving logics, which are functionally defined. That is, they are specified in terms of how and where they can operate safely, disregarding which technologies that make this possible. And within the CoEXist project, we work with the concept of 4 driving logics, where the first one, rail safe, is for very cautious vehicles which follow the brick wall stop concept and can only use predefined path and always stop if there is anything on collision course. And these mostly operate in a closed environment or when they are separated from the other traffic. And then we have cautious. Cautious means here that there is a still brick wall stop concept implemented. So they are very safe and cautious, and the gaps in the comparison with the human driver are higher. And then we have the normal driver logic, which could be which should be similar to the human behavior in terms of gaps or aggressivity. And all-knowing, where communication and cooperation is assumed, and here also a higher aggressivity in driving behavior is possible. There are many parameters you need to consider if you want to model automated vehicles, and the main uncertainty parameters considered in CoEXist project are listed here. We worked with 4 different driving logics with different AV classes and with different stages of coexistence, with different road environments and different types of vehicles. And here you can see an example of relationships between AV class, driving logics, and operational design domain, where you can have different driving logics of the same AV on different road types. So you can have many combinations which you can use in your modeling. And this was the approach used in CoEXist. A few words about impact assessment. impact assessment was based on post-processing of vehicle records, and colleagues from VTI prepared Excel sheets for automatic processing. And besides standard traffic performance metrics, like you can see here, vehicle kilometers traveled or passenger kilometers traveled or vehicle hours traveled, also space efficiency was defined and compared between scenarios like space claim or average space-time footprint. And if you are interested in more details, then I recommend you to have a look on deliverable 3.2 definitions of performance metrics and quantitative indicators. This can be found on the CoEXist webpage. The use cases we have within CoEXist project in Gothenburg in Sweden, microscopic one with shared space and accessibility during long-term construction work. That was a macro use case. In Helmond, in Netherlands, we had two microscopic use cases, signalized intersections, including pedestrians and cyclists, and transition from interurban highway to arterial. In Milton Keynes, waiting and drop-off areas and priority junction operations, microscopic use cases. And in Stuttgart, we had macroscopic use cases using Vissim and additional scripts to investigate impacts of CAVs on travel time and mode choice and impact of driverless car and ride-sharing services. From all these use cases, I picked up just one because I think it's interesting one because of the modeling approach, and that's the use case for the shared space in Sweden. Our colleagues from VTI, they adapted the approach from GIP from 2015 using scripts. And they defined a lot of priority rules within the model, also using scripts. And they used double representations of a vehicle. So vehicle is present in the model as a vehicle, but also as a two fat pedestrians there. That's why it's called double representation. And they use this approach because then you can also use the social force model and you can have an interaction between pedestrians and not only vehicle pedestrian interaction, but also pedestrian interaction. And these two big pedestrians are used to model the vehicle. For the interaction with pedestrians, they use a lot of priority rules which were created by scripts, and they use different parameters for these priority rules for a human driver and then for the driving logics for automated vehicles. So there were values for race-safe logic and different values for cautious logic and different values for normal logic. And at the end, it can look like this. You can see the short space area where pedestrians are not just crossing the road, but they can move also in the same direction as the vehicles or the opposite direction towards vehicles, and it works very well. So this was interesting approach. And we implemented also a lot of improvements for our APIs for our interfaces, for driving simulator interface and for external driver model interface. And I don't want to explain them in detail. You can find a description in the documentation, but the important message is that the driving simulator interface allows connecting Vissim to a driving, cycling, or walking simulator, and that simulator can either be simulator hardware used by a human or a piece of software representing the algorithms of a CAV or multiple CAVs. So if you have own algorithms you are developing and you want to test your own algorithms, how the vehicles will interact with the conventional traffic, this is the way you can go. There is also a possibility to use the external driver model interface, which provides options to replace the internal driving behavior by a fully user-defined behavior for some or all vehicles in a simulation run. So what does it mean, or how it can look like? There is a short demonstration of a car simulation. On the right side, you can see the Vissim network, the Vissim model. On the left side, there is a model in CarMaker from IPG. CarMaker is a software which can be used to model the vehicle dynamics and also all the sensors you need for automated vehicles. And when you connect these two simulators, then you can see how your ego vehicle interacts with the conventional vehicles provided by Vissim, and how the Vissim vehicles interact with the ego vehicle here. You can have also PT lines there, buses, pedestrians, different intersections, and you can investigate how your algorithms perform in interaction with surrounding traffic. Lesson learned and recommendations from the project. New features implemented in traffic modeling tool to allow simulation of automated vehicles, but there is still big responsibility of the modeler to define the assumptions in an appropriate way about how vehicles should or will behave. Driving logics, there is a much research ongoing, but there are still no fixed rules or standards and high uncertainties. CoEXist deliver the tools for a structured approach of assessing future scenarios and handling uncertainties, like automation-ready framework and the modeling tools and impact assessment methodology. And tools developed enable assessment of innovative infrastructure measures, but measures tested show mobility improvements mainly for high automation and penetration levels. And use case simulations show potential deterioration of urban mobility before promised benefits or CCAM are seen. Cities should plan for the transition phase. And inserting CAVs in traffic does not necessarily improve the efficiency. It depends on penetration rate and the driving logics. And we could see in the simulations that higher penetration rates and less cautious, which means more advanced CAVs, will start to generate some gains. The final event of CoEXist projects was supposed to be face-to-face meeting in Milton Keynes with a conference and a training session, but the format has been changed to an online meeting, which is good for you because you can join remotely. So if you are interested, there will be a conference stream on March 25, and there should be a workshop or training on March 26, where I will explain how to use the features more in detail, and we'll do some step-by-step exercises in the software directly. That's all from my side, and I'm happy to answer your questions.
Thank you very much, Peter. For everybody who's on right now, please feel free. There's a questions box in the go-to screen. Please go ahead and type in your questions, and we can go through some of them. Got a couple questions about slides and recording. We will be posting the slides as well as a copy of the recording. You should be getting a link in a follow-up email the next day that gives you access to that. You can also see that information on ptvtraffic.us on our resources page. We post all the previous recordings there, as well as the PTV Traffic YouTube page. So, Peter, was any thought given to different acceleration profiles of, potentially electric vehicles or anything in the study?
No, that was not the focus within CoEXist project. We explain how you can change the acceleration profiles for the vehicles. So you can assume, for example, that there will be not such high spread of different values because of big differences within the human population, but maybe the automated vehicles, they might have a lower speed and also differences in the values, but we didn't use any specific values, or we didn't recommend from CoEXist project some specific values for or specific acceleration functions. Yeah, it's always the responsibility of the modeler. Maybe later, when we will have much more vehicles on the roads, we can offer some standards functions.
Okay. Another question that came in the event at a traffic signal or some other event in the model, if a platoon gets split into two separate platoons, is it possible that if they're able to rejoin the platoon together, or once they're split, do they always act as a completely separate platoons?
If the platoon splits into two platoons, they can rejoin later again, but only if the second platoon can catch the first platoon, which means if the second platoon has a higher speed as the first one, in that case, in some time during the simulations, it can rejoin the first one. There isn't any special functionality that the first part would wait for the second part or something like that. So they act like two individual platoons after the splitting.
Okay. Let's see. I think there's a couple questions about publications regarding the calibration. All that should be available on the documents section of the CoEXist website, correct?
Yes, all deliverables will be available there. Many of them are there already. There will be some updates till the end of March or April, because the project will end in April, so all deliverables will be there available, including a guide for simulation of AVs for Vissim and for Visum.
Okay. Let's see. Were there any parts of these studies that considered emissions, or can you make some recommendations as far as ways that you could explore emission results using these features?
Sorry, I didn't get the questions.
Was there any consideration given to emissions in these studies, or could you make some recommendations?
Yep. Okay, I understand now. Emissions, no, that was not in the focus, but within the installation we provide an example with automated vehicles in a intersection, with a signalized intersection, where there is a simulation of communication, core to infrastructure communication, which means the vehicle get information about the signals, and they adapt the speed in order not to stop at the signals. So they adapt the speed, and they move continuously through the intersections, because they will cross the intersection, the signals at a green time, and this is a measure which leads to lower emissions. So you can test such measures with Vissim. There's also an example for that. But if you want to quantify emissions, in that case, if you want to be very accurate, we recommend to use NViver software, which is a product of TNO. And this product can import the vehicle records from Vissim and calculate emissions in a very precise way.
Okay, very good. The last question we got a few times here, and this is something that has come up pretty much any time we've presented on this type of topic. Can you maybe elaborate a little bit as far as why in the early stages of AV development we might see a decrease in capacity as opposed to an increase, which is what it tends to assume is going to happen?
Yes, because in the early stage, when the vehicle will be in an automated mode, it will be most likely very cautious, and especially if it will be out of freeway in an urban or suburban environment where you have a little bit more complex environment. To ensure that the vehicles can operate safely, they need to be very cautious, and you can see it, for example, on the shuttles which operate in several European countries under different projects. They all drive quite slow and only a predefined route, and if there is something in a collision course, they just stop. And I'm sure that you heard that some vehicles, automated vehicles, had problems with some erratic behavior, so they stopped or decelerate too often or too hard, even if there wasn't any reason for that, or if in the cases when the human driver wouldn't do that. And that's because they are very safe and it takes time until the technology is good enough also for more complex environment than a freeway. It might work quite well on a freeway when all vehicles drive the same direction and there is no opposite traffic. So that's quite simple or relative simple, but suburban or urban environment, it's highly complex. So that's why we think that the first or the early stage will have vehicles with which will need higher gaps for safety reasons.
Okay, thank you very much. Peter, thank you very much for the presentation. I think with that, we're going to end the Q&A portion. I know there may be a few questions still hanging out there, so we'll follow up with you in the next day or so to try to get your questions answered. Don't forget, you will be receiving the recording and the slides in a follow-up email the next day. You should also see in that email a link to join our next presentation, which is on March 19th, so next Thursday at the same time. This will be another tooltips presentation where we will be discussing a few different items. One is some basics of dynamic traffic assignment in Vissim. The next is some updates to the evaluation for SSAM, as well as covering some basics of Scenario Manager. We've also just announced there'll be another one on April 2nd, which will deal with some basics of PTV Vissim. So make sure to watch out and sign up for those webinars coming up soon. Thank you very much, everyone who attended, and we look forward to seeing you next time. Thank you and have a good day.